Okay, so we started with 2.4 last time, and we looked at our operations. So we looked at examples if you were adding two functions, subtracting, multiplying, and dividing. So that was the first part that we looked at, and we of course looked at a couple different examples. We talked about how to find their domain. Now this next part that we're getting into in section 2.4 is talking about composition. So this is also a method where you are combining two functions. You can actually do more than two, and creating a whole new function when you do this combination. But the way this actually works out is we're saying that the output of one function is actually going to become the input of another function. So you're literally taking one function and putting it inside of this another function. So the result that I get from the inner function is what I use to get, to evaluate the outer function. So when we talk about compositions, we're saying, let's say we have two functions f and g. And if I am doing a composition between f and g functions, I can say it's f of g, which basically means I'm taking the g function and I'm putting it inside of the f function. So the way this notation works is the function that I write first goes on the outside. The function that I write second actually goes on the inside. So when I'm talking about the output of one function, that means we first evaluate the inside function, that's the g function. The answer I get from it is what I'm going to use to evaluate the outside function or the f function. Now, if I switch that relationship, if I say I'm looking at a composition of g and f, which would be g of f. So again, since I'm writing g first, g becomes my outside function. Since I'm writing f second, f becomes my inside function. Now, the other important thing that we have to work with when we're doing these compositions is we have to make sure that the results that we get from the inside functions are actually going to be in the domain of the outside, because if you end up getting an answer which is not part of the outside function, you won't be able to evaluate anything at those values. So that's why it's important to make sure the results will be inside of our domain here. Now, just to show you the difference between composition and multiplication, of course, you can see in composition we use a little open circle, whereas, we just use like a dot for multiplication when we're multiplying these two functions. So remember, multiplication means I take the first function and multiply it with the result of my second function. With composition, remember what I said, the inside function's answer is what we use to evaluate the outside function. So the process is very different when you're actually working through these examples. This was just an illustration that your textbook had. So it's showing you how if you take the value of x, which is inside the domain of our composition, you first put it in the inside function. Whatever answer you get, you're going to put that inside of the outside function. Basically, the output of the g function will become the input of the f function, and that's how we're going to get our final result here. So let's take a look at this example, and we're starting out with, again, a set of ordered pairs, and then we'll build up into our equations. So number 4. Do this way. So we are defining the f function as a set of ordered pairs. We're given 2, 0, 4, 0, and 6, 8. The g function is defined as a set of 0, 7, and 6, 0. Okay, so they're asking us to figure out what the function g of f will be, and of course talk about the domain. So let's see. When we're talking about g of f, remember the function that I write first is going to be the outside function. F, the function I write second, is going to be my inside function. So this will become g of f of x. Okay, so the f is the inside function, which means we actually start with the values with the f function and then use them inside of g. So the first thing we're going to do, if you look at the domain for the f function, that will of course be 2, 4, and 6. Domain of the g function is going to be 0 and 6. So for the inside function, we'll of course start with the domain and go through all of them as long as we can use them in our outside function. The first thing we're going to start out with is f of 2. Now what will f of 2 give us? Sorry?
0.
0, right? Because you're going to the f function and finding the ordered pair where my x value is 2 and looking for the corresponding y value, which of course in this case comes out to be 0. So that's going to be my input inside of the g function. So we will get from f of 2, we get 0, and that 0 is what we're going to put inside of the g function. Now, is 0 part of the domain of the g function? Yes, it is, because we do have an ordered pair where my g of x is 0 and it gives me the corresponding value of 7. So the way you're actually going to write this is I originally started out with 2 as my x value. I went through the composition and I came out with 7 as my final answer. So the ordered pair for your composition function starts at 2 and ends at 7. So you go with the very first value that we began this process with. Obviously, we're going to repeat that with the other values from our f domain. So our next one will be g of f of 4. So again, you're looking for f of 4. What will that come out to be? 0 again, right? Because I'm going to the f function, finding the ordered pair where x is 4, the corresponding y value is 0. So again, g of 0 will take me back to the same exact ordered pair, and I'm going to get g of 0 as 7. But what's the ordered pair for our composition going to be?
4, 7.
Yeah, because we started out with 4 and ended with 7, so this is my second ordered pair for the composition. Now, what are we going to get with 6? So if we did g of f of 6, where does f of 6 take us?
8.
To 8, yeah, because that's the ordered pair, 6 and 8. Now, do I have g of 8 in my domain for g? No, I have a 6, but I don't have an 8 because I cannot find an ordered pair where my x value is 8. So I actually have no answer for g of 8, which means I cannot include that as part of my function here, which means our g of f function, or I guess we don't really have to write it with x since we're writing these guys as ordered pairs, is going to be the set of 2, 7 and 4, 7. Because that's all I could get out of it, right? What will be the domain for the composition function? For this guy?
2, 4.
2 and 4, yeah. So the domain of g of f just those two x values, 2 and 4. Okay, questions on this example? And that's all they were asking us to figure out was what the function would be and then what the domain of that function would be. Now, changing it up a little, if we are talking about in terms of equations, then how will our process change? So let's take a look at example 5 here. So this time we are given g of x as square root of x minus 1, h of x as 2x. What will be the domain for each of these individual functions? So what will be the domain of the g function? Uh-huh.
1. And then to infinity, right?
Yeah, so remember you can have a 0 inside of a square root, you just cannot have a negative. So if we make our x value as 1, 1 minus 1 gives us 0. So you can start from 0 and then of course go towards positive infinity. What about domain of the h function?
Negative infinity, positive.
Yeah, all real numbers because it's a straight line. Negative infinity to positive infinity. Okay, so here they are asking us to find g of h at 5. So they're specifically asking us to solve this at the value of 5. What do you think that will give us? So again, remember the way compositions are written. G will be your outer function. H is going to be the inside function. So this will be g of h at 5. So start with the h function, evaluate that at 5, which will give you, 10, right? Because you're doing h at 5, which becomes 2 times 5. 2 times 5 will become 10. If you want, you can do it as a little, I guess, scratch work on the side. So you know where you got the 10 from. And then what will be g of 10? And is that part of our domain, first of all? Can I use 10? Yeah. I can because it's well within that 1 to infinity range. So g of 10?
It's not a happy number.
Is that a happy number? You sure?
Oh, wait a minute.
I think it will be because you are doing square root.
Minus 1, sorry.
Yeah, 10 minus 1, which comes out to be 9. Square root of 9 will give you 3, right? So in this case, we end up getting what as our ordered pair?
5 coming 3.
Yeah, you started out with 5, and then finally ended up with 3. And I think they're just reversing the order for the second part, and that's going to be h of g at 5. So let me see what you guys come up with for this guy. So h on the outside, g on the inside. So h of g of 5. What will that give us? Do you have an answer, Jeremy? No? Maria? 5 and 2 as our ordered pair. Did we get 2 as the final answer?
5 and 4.
Yeah, that's right.
You got 5 and 4? Okay, so obviously we're starting out with g and 5, so let's see if we get 2 or 5. G of 5, which means you're going to the g function. That's going to be square root of 5 minus 1, of course, square root of 4 which ends up giving you 2. Now this 2, of course, becomes the input for the h function, right? So that's going to be h of 2. H of 2, of course, comes out to be 2 times 2, which gives you 4. So did you stop here?
Yeah.
Yeah? Okay. So obviously we started out with the 5 and we ended with the 4. Okay? 5, 4. So this was an example where they wanted us to find the answer at a specific given value of x, which in this case, in both compositions, they wanted us to do this at 5. But let's look at what happens next here. Okay, so in example 4, which was the set of ordered pairs here, right, this example, they're telling us the domain of g of f came out to be 2, comma 4, whereas the domain of the f function was 2, 4, and 6. So they're saying to find the domain of the g of f, we remove any number from the domain of f, which is not going to end up in the domain of the g function, right? And that's why we excluded that 6, because the 6 was not giving us a comparable ordered pair. So obviously we always have to remember that kind of thing when we're working with these compositions. Now here, we're doing a general example. So they're giving us f of x as square root of x plus 3, g of x is 3x, very similar to the example we just did. But instead of evaluating at a specific value for x, they're just saying find f of g and talk about its domain. So in general terms, what's going to happen with example 6? Go ahead and tell me what the individual domains for these functions should be.
Domain of f of x is going to be
Go ahead.
bracket -3 to infinity. I think.
You said -3 to infinity?
Yeah.
Okay, so do we agree with that for the f function? Yeah, because -3 again will give us 0, right? If I did -3 plus 3, I get 0. Square root of 0 is of course 0. So starting at -3, we're going to positive infinity. For the g function,
Negative infinity to positive.
yeah, again, it's a straight line. So you are going from negative infinity to positive infinity. Now in this example, they're asking us to find f of g. And since we're doing this in generic terms, we'll definitely use the x as part of our function notation. So here, f is the outside function, g is the inside function. So since we're doing this in general terms and not actually evaluating at a given value of x, that literally means in my f function, I am going to replace wherever I see an x with what's my g of x function, and in this case, that happens to be 3x. So everywhere that I have x in my original f function, I am going to replace it with 3x. Just like we had done in this first section of chapter 2 when we introduced the function notation. So when I rewrite my f function with 3x, what will I end up getting?
Square root of 3x.
Yeah, like I said, everywhere that you see x, you're replacing it with 3x. So this will actually become 3x plus 3, and this is our definition for the f of g function. And domain. So how can we figure that out? So what's the general process? And I've mentioned this a couple of times in class before.
-1.
how do you find out the domain when you're looking inside a radical? The easiest way, if you're trying to plug in numbers and figure out what's going to give you 0, other than that, the easiest thing is take what's inside the radical and set it equal to 0 to figure out where it becomes 0 at. So in this case, you would end up with 3x plus 3. Set it equal to 0. Get your x by itself. We start by subtracting by 3. Divide by 3 to get the x. We get -1, right? So when I put -1 in for my x, -1 times 3 becomes -3. -3 plus 3 will become 0, right? Which means our domain starts at -1 and goes towards positive infinity. So that's the easiest way to figure out what your domain is going to be when you're working inside a radical. And that's the same thing you could have also done right here, taken your x plus 3, set it equal to 0, which would have given you -3 as your starting point, and you would have had -3 to infinity. So anytime you're working with radicals, to figure out where your domain is going to be. So in generic terms, our function definition for f of g is going to be square root of 3x plus 3, and then its domain is going to be from -1 to infinity. Any questions on 6? Okay. So this was actually us taking two individual equations and putting them together. Now the idea is sometimes you can think of some of these complicated functions actually being compositions themselves. So if you're looking at a function like this, capital F of x is x minus 7, the whole quantity squared. You can actually think about this as being a composition of two separate functions. So they're saying, just imagine if you were, having to plug in a value for x. The first thing we would do is take that value of x, subtract 7 from it, whatever answer we got, then we would square it, right? Because here you're basically using your order of operations where we work inside the parentheses first and then do what's on the outside. So I would subtract the 7 first and then square it. So those two operations actually become two individual functions. So x minus 7 becomes one of the simpler functions, and just the square becomes another function. So you have x squared as the g function and x minus 7 as the small f function. And in this case, your composition is actually working in the form of g of f, where g is the outside function, f is the inside function, because I subtract first and then I square. But let's say you change that order and you make it f of g. That means I'm actually going to square first and then subtract 7, and you can see I end up getting x squared minus 7 and not the same thing as x minus 7, the quantity squared. So when you're working backwards, where they're giving you the bigger function and they're asking you to break it down into simpler functions, order is very, very important, because you have to make sure that you're setting it up in the right order, because otherwise you end up getting two different functions and you didn't end up with the original function you started out with. So those are actually the next set of examples that we're looking for. I have one here, but I'll give you one extra one to work on just to make sure you are comfortable with this. So our large function is 2 times square root of x minus 3. They're actually asking us to break it down into 3 simpler functions, so f, g, and h. So what will those 3 simple functions be? So that's our composed function, I guess. And they're asking us to define 3 individual functions. So remember, for each operation, basically, you should have one function. So think about what are the three different operations happening when I put something in for x. Okay?
Does the order that the operations happen in have to correlate with what?
No, because you can always write it as f of h of g, or you can switch those around. So just define your three functions as you want to. So when I first plug in the x in there, what's the first thing we're going to do with the x? Subtract 3. So that means subtract 3 is going to be one of my operations or simpler functions. What would be our next step after we subtracted that 3?
Square root.
Take the square root, which means square root of x is going to be our second function.
Where are you getting the square root of x versus not x minus 3?
Because I already defined x minus 3 as a separate function. I don't need to repeat it.
So I'm wondering why are you just taking the square root of x and not like the square root of x minus 3?
Because that's when the composition will put this x minus 3 inside the square root. So we don't need to define it. Because remember, we're just defining these as simple functions, which means each operation that you do has to be a separate function. Go back to that example that we just looked at with the, x minus 7, the whole quantity squared, right? I only defined x minus 7 as one of my simple functions, and the square did not have an x minus 7 in there. It was just a square function. So each operation is going to be defined individually. So in our example, x minus 3 gets one function, but then I don't need to repeat it when I'm doing the square root of x, because that's the same thing as I was doing the second operation, in this case x squared, in our example square root. So you don't need to repeat the inside function every time you are defining your simpler. That's the one thing you really have to kind of differentiate between. Once I do all my compositions, I should end up getting that bigger function, but each individual does not need to have repetitions for all those operations. Where were we? Okay, so we've got x minus 3 as the first operation that happens, because once I plug in a value for x, the very first thing I'm going to do is subtract 3. Just imagine, you can just put a 3 in there for your imaginary value of x, because x can be anything as long as it's in the domain of that function. So I would first subtract whatever value of x I have with the 3. That answer that I get, the next operation I will be doing is square root on that number. So that's where the square root of x is coming from. So what do you think that last h function should be defined as? Multiplying by 2. And since we're multiplying by 2, again, since this will be building up into a composition, you just do 2 times x. Again, you don't need to write out the entire thing. Each individual person will have their own definition for f, g, and h. So it's not necessary that your definition would match your friends or your classmates, but how you do your composition, you should still end up in that same function format. Okay, so in our case, we are defining f as the x minus 3. That's got to be our innermost function. So once we do x minus 3, then we need to take the square root, which means g will be my next function in line. And then the very last thing on the outside that we do is whatever answer we get from here gets multiplied with the 2. So that's actually going to become your outermost function. So as I said, that order is really important, because if we set it up in f of g of h, you're actually going to end up getting a completely different example, and I'll show you that in our scratch work. But obviously we want to make sure that this order will get us to the function we started out with our capital K function. So let's go ahead and break this guy down. So we've got, let's see, h of g of f, and f we're defining as x minus 3. So remember now, x minus 3 is going to replace everything in the g function where you see an x. So now I'm going to take this x minus 3 and put it inside the g function. The g function we defined as square root of x. Instead of x, replace it with x minus 3. Now this is the input for h, right? Which means all of this is going to replace the x. We don't really need it under the t. But everywhere you see an x in the h function is going to get replaced with this entire thing in the parentheses, which is square root of x minus 3. So that will end up giving us 2 times x, but instead of x, we're going to have square root of x minus 3. And if we are successful, we should be coming back to the capital K function. And we are. So this now equals capital K of x, which means we did our composition correctly. Now, as I was telling you, if we didn't set the composition correctly, let's say we went in the order of f of g of h, that means h is the innermost function right now. And if h is the innermost function, that's your 2x. 2x is what's replacing the x inside the g function now. Your g function is square root of x. So I'm replacing my x with 2x. It will now become square root of 2x. And you can see, obviously, we're not going to end up with the original k function here. Now, the square root of 2x is going into the f function. Our f was defined as x minus 3. So that will actually now become square root of 2x. And then on the outside, you have minus 3. And then, you know, of course, if you change the middle function to g of f of h or any other combination, you're going to get something completely different. So this order is really what's crucial when you are breaking them down into simpler functions and then trying to define what that composition would look like. So let me give you one more example for this composition. So let's do cube root of 3x squared plus 1. And again, you are defining three individual functions. So for each operation, you should have one function. So take a couple minutes and tell me what those individual functions should be. Okay, so instead of defining this in 3, we're defining it with 4, since we do have 4 different operations here. So remember, you start with the innermost. If I plug a number in for x, what's the first thing I do? And that's, of course, going to be we square. Okay, that's the first operation. Now, after we have squared this number, what would happen next? Multiply by 3. So that's where just 3x, right? Not 3x squared, just 3x comes into play. So we've taken care of the square. We took care of the multiplication by 3. What's the next operation that'll happen?
Add 1.
Add 1. So that's again just x plus 1, which brings us to the very last one, and that will be the cube root. Very good. So again, it will be just cube root of x, because when you do compositions, you're bringing all those previous ones in there. So depending on how you define your f, g, h, and j functions, your order might be a little bit different. But the cube root has to be the outermost function. So whichever one you defined as your cube root, that's got to be the outermost, which in my case, that would be j. Then the next step would be is where we add it. So whichever one you used as your plus function is going to be the next in line. Then of course multiplying by 3. So whichever one is your 3x, that should be next. In my case, that will be g. And our innermost function in this case, so let's see, that's 1, 2, 3, 4. That's a parenthesis. And if you guys have done programming, you know how important those parentheses are. You drop one, and your computer goes completely bonkers. Alrighty, so we're starting with the innermost function, which is f of x. So that's going to be j of h, j of h of g, and the input for g is going to be the x squared function. So that means everywhere that I have an x, I'm going to replace it with x squared. So that will end up becoming j of h, g of x squared will become 3x squared. So you can see we're kind of building up on that first part of the 3x squared. Our h function is the addition plus 1. So that's where I will have j of, and then h is now going to get 3x squared as its input. So that will become 3x squared plus 1. And then now you can see this guy becomes the input for the j function. So all of this is going to replace the x in here, giving us cube root of 3x squared plus 1, which basically took us back to the original function that we started out with. So you will definitely see multiple different examples of this in my MATLAB. Some of them may ask you just to break it down into 2 simple functions, 3 simple functions, it'll just depend. But again, remember how you define each individual function is not as important as making sure the order of your composition is correct. So this is the part you really have to be careful about, the j of h of g of f, how you write it out. Now, if we were writing this with our composition notation, this would actually end up looking like j of h of g of f of x, okay, in the composition notation. Okay, so this was our example, but any questions on this one or also on number 7? Any questions on these 2 examples? Okay. Let's go back to our handout. So that brings us down to our last 2 examples. Here we're talking about applications with compositions. So this one is talking about write the area A of a square with the side of length S as a function of its diagonal, D. So how do we write the area of a square that has a side S in terms of its diagonal, D? That's our diagonal, this is our side. How do we define the area of the square? Yeah, side times side, right? So S squared. So the idea is, how do I go? The composition here is happening, is where I'm going from A in terms of S and rewriting A in terms of D, which is the diagonal of our square here. We actually did this very same example, section 2.1, when we talked about constructing functions. So since I'm going from A, written in terms of S, and from there I need to go and write my area in terms of D. We first need to figure out what's the relationship between the diagonal and the side of a square. So what information can I use here?
Isn't that you're figuring out like the area of the
Sorry?
It's like trying to figure out a triangle, right? 'Cause you're trying to figure out like
You
C,
can.
basically, so it's like a squared plus b squared equals c squared.
Yeah, and do you know what that's called?
Oh shoot,
Pythagorean.
Pythagorean.
Yeah,
Theorem.
you're basically using the Pythagorean theorem to define what's the relationship between the diagonal and the sides. So of course the diagonal becomes the hypotenuse, right, of the right triangle. So that's actually going to be d squared equals side square plus side square. What does that simplify into?
Equals 2 side squared.
Yeah, s squared plus s squared will become 2s squared. So we have now defined area in terms of side and diagonal in terms of side. Now where will that composition happen? Where I bring in one function and put it inside of the other. Right in front of you. Where does that transition happen?
S is a so S is your innermost term? Or side is your innermost term? So 2s squared.
In a way, yeah, you can think about it that way. Because right now the input for D is coming from the S, right? And we want to change it from the S to an A. Yeah, because they're saying write the area as a function of its diagonal. Robert?
So since s squared is also equal to a, couldn't you just replace it with a?
Very good. Yeah, so this is actually where that input is coming in terms of A, because you can replace your S squared, because S squared is already defined as A. Let's get this guy down. Okay. So this is where we're actually going to replace our S squared in terms of A. Remember here the relationship we're using is A equals S squared. Now, this is asking us to write A in terms of D. So what do I do to clean this up?
A equals, well, you divide it by 2, so you get A equals d squared divided by 2.
Right, very nice. Get A by itself. So you're actually going to end up getting A equals D squared over 2. So this is what they're asking us to do here in terms of our composition. Pretty much the same exact thing is happening on example number 9, but before we go on to 9, questions about 8? Oh, stop doing that. Okay, here we're talking in terms of revenue and commission, I believe, yeah. So the revenue for a sale of X books at $80 each is given by the function R of X equals 80 times X, right? So for each book sold, the revenue that's coming in is $80, so that's 80 times the number of books sold. The commission for the revenue is based on X dollars, and this is based on given by the function C of X equals 0.10 times X. The difference is in revenue function, the X represents the number of books. In the commission function, the X represents the dollar amount, right? They want us to write the commission as a function based on the number of books. Now, how much commission are you earning when the function is 0.10 times x? 10%, right? And that 10% is based on revenue. So are you seeing how that transition is going to happen, that we can write the commission function based on the number of books?
$8 a book.
$8 a book, so how did you do that?
If you did 10% for every book sold, and each book comes, or $80 comes in for each book. 10% of 80 is going to be $8.
Yeah, so you're actually going to take the revenue function and you're going to put that as the input for the commission function, because revenue is based on the number of books and we want to rewrite commission based on the number of books. So this was number 9. The revenue function is defined as 80 times x, where your x represents the number of books. The commission function is at 10% commission on your revenue, where the x is defined as the dollar amount from your revenue, right? So to rewrite commission based on the number of books, you are actually going to input the revenue function inside of the commission function. So that's going to be C of R of X, which will be C of 80X, right? And then again, that 80X is going to replace the X inside our commission function, which will come out to be, that should be 0.10 multiplied into 80x, but now remember your x represents the number of books because it's coming in from the revenue function, and it's going to become 8x, and here the x are, technically it should be the number of books sold. So here again, they're not asking us to evaluate at a given amount or anything like that. This was just talking about doing your composition in general terms. Any questions on number 9? No? Alrighty guys, so that will be the end. 1, 3, 1.